Welcome everyone. We are Team VegaPod Hyperloop, and we are here to walk you through the design process of our propulsion subsystem, along with showcasing my team's work from past a year. I'll also hope that we'll be able to convey our ideas to its best, especially to those who are unfamiliar with the domain. Uh, Along with that, I will also like to give you some awesome insight into the design and manufacturing process of our subsystem and the decisions we made and why we made them while designing. So without wasting much of our time, let's hop into the presentation with our power system lead, Rupesh.
Propulsion is one of the important department of our team. So basically propulsion is a means of creating force by which our pods move. It can be mainly found by two things. One is contactless propulsion system, while the other one is contact propulsion system. In contact propulsion system, basically track and our pod is in contact with each other, while in contactless, they are having some distance. So before we start any project, we all must have some aim. So while designing our pod, first aim was to have a contactless propulsion system because our first pod was a contact one because we were using BLDC motors, that is brushless DC motor. And our second aim was to reduce as much cost as possible. So while manufacturing, we consider various things how we can reduce our cost and all. So as I said earlier, we were using contactless propulsion system. So there were various options available to us, like to use linear synchronous motor or linear induction motor. But we decided to go with the linear induction motor as it was meeting most of our criteria. So if we talk about our basic principle of linear induction motor, it has two parts, primary and secondary. Primary is basically coil and core, and secondary is aluminum plate or track. So if we supply balanced three phase to the primary, a moving magnetic field is induced. Because of that moving magnetic field, a current is induced in the secondary, and that current create a magnetic field which tries to move with this synchronous speed. So basically it propels our pod. So designing the pod, there were some things to meet the criteria, like target speed of 75 km per hour was one of our target. So we calculated the force required to take to 75 km per hour. It was coming out to be around 300 newtons. Also, one major factor was that we tried to reduce the weight of linear induction motor as much as possible. So the weight of 7 more than 10 kg was not that good. So we decided to go with less than 10 kg of our weight of linear induction motor. Also, there was limitation of like we can't use so much of battery. So we would try to achieve all these things in less than 9 kilowatt of power. So these are our action plans. First, we created a pod trajectory, like which includes speed, weight, force, and etc. Various parameters are included in the pod trajectory. Then we started designing our motor. We did hand calculation, then simulation on various apps. We got magnetic fields where it's increasing and decreasing. We also find out the current density and etc. Then we started manufacturing the motor. Then we tested our motors in our lab, like we tested the how much current is withdrawing and all that things. And if we find any difficulty in certain things, then we rectified that also.
So, following the hierarchy of our action plan, we would now discuss the pod trajectory. The pod trajectory was calculated keeping in mind our track length of 200 meters. The pod trajectory as you can see on your screen, at t is equal to 0 seconds, we gave a constant acceleration to our pod of around 3.1 meter per second until it reached the constant saturation velocity of 20 meter per second. At around 145 meter, we actuated the brakes so that the pod starts to deaccelerate until it completely stops at around 160 meters. So the next section of our presentation would be on our pod design, under which we would first discuss the slot design. We actually had three options to go with: semi-closed, open slot, and closed slot. We went for the open slot design because semi-closed are a bit complex to mount on, and closed slot was a bit expensive to manufacture. But uh, design details were the parameters of the design details were calculated according to the prerequisites, which was to achieve a thrust force of 300 newtons and to avoid saturation of our core. So these are the some of the parameters of our LIM. Length was 450 mm, width was 60 mm, height of 50 mm, and weight of around 8.5 kg. Analysis of magnetic flux density. So, as we all know, magnetic flux density is a key parameter in any kind of a motor, be it a linear motor or a rotatory motor. Thus, here we have simulated the magnetic flux density. In an LIM, the rotating magnetic flux density, actually linear rotating magnetic flux density, induces eddy currents on the stator, which makes the stator to act like a magnet which with varying polarities, which tends to follow the rotating magnetic field of the LIM. As you can see on your right, we were actually able to produce a magnetic flux density of 0.6 Tesla, which was less than the saturation, the threshold value of 1.6 Tesla, which meant that our slot width was wide enough to actually avoid the saturation of our core.
Hello everyone, I'll be taking you through the manufacturing process of our linear induction motor. So as you all can see on your screens, the silicon sheets are being water jet cut. So to cut the silicon sheets, we went through various options. So other options like stamping and laser cutting were considered. But the issue with stamping was that the using cost of the machinery was extremely high. And in laser cutting, the edges were being warped up. So we decided to go with water jet cutting. Here you can see the S3015 waterjet machine, which we used to cut the silicon sheets. So now we come to winding design. So the winding was designed for a high current, higher thrust motor. So while designing a motor, you can either design a motor for a higher current value or a higher thrust voltage value. And in our application, we decided to go with a high current motor. A single turn concentrated lap winding was used. So this is actually helpful if we want higher torque values at lower speeds. The peak current of our motor was at around 100 amperes and the nominal current was around 36 amperes. Also, the windings were insulated properly to avoid any failure. So when you are using a motor, you don't want the R, Y, and B phases of the motor to come into contact. And hence, to avoid any such failures, we ensured that the windings were insulated properly. Here you can see an image of our motor which is mounted on the pod, and you can see the stability system which consists of the wheels and other things as well. So guys, now we come to one of the most important parts of our presentation, which is the budget. And as you all can see on my bottom right, the total budget, including the manufacturing and testing, was just $335. Now, I guess you might be wondering that I am missing a couple of zeros here, but that's not the case. We actually managed to completely manufacture and test our linear induction motor in just $335, where the majority of chunk was spent in water jet cutting and purchasing the silicon steel sheets, and then the other part was spent in the coil windings and some further testing part. Testing.
So testing. So here we would experimentally observe and verify our parameters. Coming to the coil resistance test. So here what we did is we connected the input end of the LIM to a micrometer and the other end was connected to neutral. Thus, doing this, we now observe the resistance value with respect to the neutral, which was about 32.8 milliohms for R, 32.4 milliohms for Y, and around 31.7 milliohms for V phase. Power supply test. So in this test, we actually supplied a input power to the motor and check how much the motor draws the current at the rated voltage. So for doing that, we first connected the RYB three phases of the LIM to RYB of the supply, and then we slowly increased the voltage until we reached a voltage value of 252 volts, which was the rated value of our LIM using a demostat. Then we observe the current drawn by the by the LIM at the rated voltage. Here we showcase a video of our testing. We observed current drawn the observed current drawn was 15 amperes at no load. Since the motor was designed for carrying 80 kgs of load, the current drawn was less.
So now guys, I'll take you to the LIM on-track testing. So here actually what we wanted to do was how we wanted to see how our linear induction motor works when we interface it with the chassis. So what we actually did was we took the chassis, we mounted our linear induction motor on it, and then we mounted our stability system as well. We then kept the setup on an I-beam track. We have used the material track which we use is an aluminum 601 track, and so what we do is we give three phase electrical supply to the motor, and using demostat we slowly increase the voltage value, and we then observe how the basically how the induction motor works, what current it draws, what voltage it draws. So it was beautiful. It's like you have worked all year long, you have designed, you have manufactured your motor, and then you can finally see how it runs when you interface with the chassis. So what we observed here was a peak current was around 100 amperes was drawn, and the continuous current drawn was around 35 amperes. So as you can see on the test setup, the chassis is kept on the I-beam track, and then the motor, which you may not see, but it's mounted on the bottom side of the chassis. Here you can see an image of a linear induction motor. So in the previous slide, I mentioned that you cannot see the motor. So this is how it actually looks. So an air gap was of around 5 millimeters was kept. And this is actually a photo we have taken while we were running the motor on a test track back at Pune. So yes.
I hope we were able to convey our ideas with clarity. Now I would like to thank CHC for organizing such a conference and give us an opportunity to present and convey our ideas and contribute in this conference. Along with that, I would like to thank everyone present here for lending us a station here.